Hey, once again. Yeah, thanks again for checking in and again and again. I say it all the time, but I'm serious. I totally respect your time and your efforts in watching these crazy talking to myself videos. This one is, man, this one could be long. I gotta talk quickly. It has the topic is titration curves. As you're adding a strong acid to a strong base to a weak acid, etc., etc., what happens to the pH as a function of how much base you've added or how much acid you've added? They're very common. It's a common question in chemistry, so I would expect to see one on the midterm 3, on the final for sure. Many courses talk about titration curves. The story goes something like this. I have a strong acid, maybe 50 milliliters, zero point 0.1 molar HCl or something like that. And I titrate it with probably 0.1 molar NaOH just to keep things simple. And in the beginning, the pH comes up a little bit, but only because I'm canceling some of the acid with some base. But as you see, the pH takes a long time to crawl upward until all of a sudden we reach a point right in this area where my base has canceled my acid directly, exactly. Let's see, 50 milliliters times 0.1 mole, that's 5 millimoles. So if I had 5 millimoles of acid here, once I've added 5 millimoles of base, then the pH jumps like immediately, drastically, quickly up to a pH of 7. You should memorize that a strong acid plus a strong base gives neutral water, and the pH at that point is 7 at the equivalence point. Honestly, most of the calculations down here and up here are pretty simple. It's just a strong acid, strong base mixture. And so maybe I'll run through one calculation here, maybe one up here if I get a second. By the time you go beyond the equivalence point, I have added too much base, and my calculation is just that of too much base or an excess base in a certain volume of water. For example, in region 1, if I had, oops, wrong way. If I had, let me pick the 20 milliliter mark. If I had a 20 milliliter 0.1 molar NaOH to 50 milliliters of 0.1 molar HCl, that's 2 millimoles of strong base, 5 millimoles of strong acid. In other words, 2 millimoles of strong base cancels 2 millimoles of strong acid, leaving 3 millimoles of strong acid behind. My total volume was 20 milliliters plus 50 milliliters is 70 milliliters, and 3 over 70, I believe, is 0.043-ish. And that's the millimoles over milliliters, or molarity of H+. And if I take the negative log of that, that gives me the pH. That's a mouthful, but you can study the PDF, you can rewind the video. And up in region 2, when I've gone beyond the equivalence point, where I've added too much base, 70 milliliters of NaOH, 0.1 molar, 7 millimoles. So, and I started with 50 milliliters of 0.1 molar acid, 5 millimoles. So 7 millimoles is 2 millimoles of base too much. Or in other words, the 7 cancels 5 of these, cancel 5 of those, giving me water, which doesn't matter much. The total volume is 120 milliliters, and the millimoles of base left over. And I take the negative log of that. And that's, don't forget to subtract from 14 because my pH is now very high. And again, memorize the equivalence point being 7. Strong acid, strong base, neutralization. 5 millimoles of this, 5 millimoles of that. Neutral water. Alright, fine and dandy. Oh, one more by the way. It also works for titrating a strong base with a strong acid. So if I'm adding HCl, the pH comes down a little bit, but my base is so strong that I have not canceled all the base moles of base yet, and I have a high pH until a certain point where right about here, let's see, this could quite possibly be 25 millimoles of strong acid and 25 millimoles. Ooh, interesting. I should relabel that, perhaps. Anyways, not a big deal. Calculations are done the same. Whatever you have excess of, that's what dominates. But now here's the really tricky part. Tricky part starts to happen when I have a weak acid. Here's a weak acid, 25 milliliters of 0.1 molar, or it doesn't even matter what the molarity is. All I need to know is the shape of the curve and how much base I've added, and the pH. I should know the pH, or I should know the Ka of the weak acid. Anyways, the main difference is right here. The pH climbs a lot faster with my weak base. With my weak base, the pH comes up faster. I'm sorry, my weak acid, and I add the strong base. My pH comes up more quickly, and there's something funky going on here, and that is it's a buffer region. I'm creating a little bit of a conjugate base for that acid as my NaOH titrates or cancels my H+. Interesting. This appears an easy calculation. It's just the same old excess OH minus and however much water you have. This may actually be the most difficult calculation, but I know that my pH is going to be more than 7 because my strong base sort of overwhelms my weak acid. This one's an easy calculation as well because it's just my old school weak acid problem in the water. This one's my new interesting buffer equation called the Henderson-Hasselbalch equation. So again, maybe I'll do a calculation here. Maybe I'll do a calculation here in what's called the buffer region. I'll do this one as well, but this one up here I'm going to leave alone, which is just too much. No, it's too much. Not enough time. YouTube limits me to 15 minutes, so that's what I'll stick with. Plus, who has the attention span beyond 15 minutes? I don't. All right, region 1, weak acid, old problem. Guesstimate the Ka because I don't really know the formula for the acid, but there's a trick I can tell you during lecture about how to look at this region and find the Ka. But in any case, maybe you'll guess it if I make it to the end of this blah blah. So I know my Ka. I don't know my molarity of H plus and A minus, but I can find that assuming X is small, assuming X is small compared to 0.1, which is pushing it. Look at this. Anyways, 0.0039 or 0.004 compared to 0.1. I believe that's probably 4% dissociation, but I'm going to squeak by with this approximation. So I've seen that before. But the buffer region, you've also seen before, but you haven't seen it phrased in this context. As the OH minus is converted some, but not all of the original weak acid to its conjugate base, I have some of this remaining, but I have created some OH minus. Let's say that I've titrated a little bit of this to create some of this, and I'm just going to say 5 milliliters of 0.1 molar NaOH. So I'm talking right here. What's the pH right here? If I had 5 milliliters, 5, 10, 15, 20, 25, 5 milliliters of NaOH to write this right here, I know the Ka of the acid. I should be able to imagine the buffer equation. And let me show you the hard way. I call it the difficult way. 5 milliliters of 0.1 molar NaOH added to my 25 milliliters original of 0.1 molar HA. And let's see, that's a half a millimole, and this is 2.5 millimoles. So I'm adding a half a millimole of strong base to my original acid. This goes away totally. This goes down by half a millimole. This goes up by half a millimole. I really don't care about the water, though. But the thing now is this. I've created a little bit of conjugate base, just 0.5 millimoles of it, from my original 2.5 millimoles of weak acid. So my ratio of newly created conjugate base to my old leftover HA acid is 0.5 to 2. In other words, 1 to 4. Is that right? I think that's right. Anyways, do the math. And the pH comes out to 3.2. But you know what? There's an easier way. It seems like it wouldn't work, it shouldn't work, but it really does. The easier way is to compare the volumes of all things. If the volume of the base to titrate to a specific quantity of acid is known, this known amount of volume of base is a relative measure of how much old acid I have compared to the conjugate base. It took me actually, you want to know the truth, months to prove this to myself. I'm still freaked out by this, that it works like this. From the graph, 25 milliliters of NaOH titrated to completion. So if it took 25 milliliters of NaOH to titrate my weak acid all the way, then if I know my Ka, I can use this as a relative measure of how much acid there was in that mixture. Here, I wrote it out this way too. Portion of the titration that got done already, and that's just to 15 milliliters. Portion of the titration not done would be, if it took 25, it's the difference between 25 and 15. It's like a simple subtraction. And again, this just freaks me out, like it should have worked like this, but it does. In a way, I'm using volumes. This volume is the total volume of titration. This is the portion of that full titration that I've gone in, say, my second titration. So often it'll involve 2 titrations in the lab. So a relative amount of how far I've come to how far I need to go still. And do the math, and it all comes down to this. So I suppose if I added 5 milliliters and my pH went to 3.2, 5 milliliters of a base went to 3.2 pH, that if I go a little bit further to 15 milliliters, my pH will come up even 15 milliliters. My pH will come up even a little bit further, 3.6. I could write that in a little picture. I could say, well, if 25 milliliters went to the full way, but I only gone to 15, then I have created this amount of conjugate base, but I still have this amount of weak acid remaining to go. That seems like it shouldn't work, but it does. Oh my goodness. You know what? I'm going to skip. Shoot. Hang on, let me pause this and think about this for a second. Yeah, thanks for pausing. Thanks for waiting. I have decided to skip this region 3. This region 3, the equivalence point pH of titration with a weak acid strong base, it's kind of gnarly. I mean, there's nothing we haven't done before, but look at it sometime on the PDF. I don't know if I'll ever have time to make a video explanation of it. Maybe I should. And to rephrase, here's a different titration. So this right here, if it took 50 milliliters to titrate my weak acid, then this portion is 50 minus 20 still to go. So I have 30 to go from here to here, and 20 has been done. It's an interesting idea, but it works. So, story. An unknown acid titrated by an unknown student in an unknown lab, in unknown Chem 1215 section, unknown state. Ha, kidding, so many unknowns. Oh, what in the world? That's not proper English. Something, blah, blah, blah. Unknown, okay. I better fix that. Anyways, there's just a lot of unknowns, but you know what? You don't have to know much. We have this unknown acid, but we have a, oh, I see what I said. A set, specific, yet unknown portion of this acid was titrated twice, once to the equivalence point and once partially with a pH meter. The full titration took 37.95 milliliters of NaOH, but the second titration only went to 11.5 and tested the pH at 3.74. With this only, we can find the pH. Here's the picture. Cool picture. It's just a sketch. So 37.95 to the full blown and only 11.25 tested at a pH of 3.74. From this graph alone, we can tell the Ka of that weak acid. It's a crazy idea. But again, those numbers were 11.25. That's how much of the conjugate base I've created in the water. But still to go is, the relatively speaking, the difference between the full blown amount and where I stopped. And the 3.74 pH comes in right here. 3.74. Yeah. So just a little bit of rearrangement, a little bit of algebra, and voila, we have it. That's just a crazy idea. I can find the Ka of an unknown weak acid with just the knowledge of the titration. And I don't even know that how much volume of weak acid. I know, I should know how much volume of weak acid solution I start off with, but it doesn't really matter. I mean, it could be 10 milliliters, it could be 20, it could be 50 milliliters, it doesn't really matter. All I need to know is if I have a convenient amount of base to titrate it, then I stop at midway, measure the pH. That's just a crazy idea. Have I said crazy before? I think I'm going crazy. I'm talking to my computer. If you're watching me. Thanks, guys. Take care. See you in class.